Okay, so the Zoom session for today, finishing up chapter 14, there's been the reading and practice problems posted. There's been 3 videos, mostly on the stereochemistry stuff. So the thing is that when we switch textbooks, this was one of the things that's not covered as well in the new textbook as in the old. So it's mainly covered in the 3 videos, quite in depth, I will say. It's really only the last section of chapter 14, but historically and according to our curriculum, this is the most important part of this part of the course. So we need to cover it, and I may put up a few more extra postings on that. Maybe some extra reading, but I think really the videos cover it. Look for additional postings, possibly. Okay, so hopefully you've seen video 3 by now for the later part of this. So the only other really important part was the reaction chemistry of alcohols. That is really the reverse of addition to alkenes that created alcohols. When we added water to an alkene, so if we had an alkene like this, something like this or whatever, and we added water to it, it added an OH to one of the carbons and an H to the other carbon. So in this case, it would be probably preferred to be like this. These, what we're seeing here, are the reverse reactions, the dehydration. So removing water. So if you look at the first example here, one thing to be aware of is that these parts of molecules that are like benzene rings here are pretty much unreactive. So really it's just a spectator, and all the action is going to take place here. The reaction is the removal of OH and a hydrogen from the adjacent carbon. Here's the adjacent carbon. Remember, there's a carbon there. So we remove OH and H from the 2 carbons. There is no hydrogen here to be removed, so it can't go in that direction. So our product for this is going to look like this, where all of this is a spectator and unchanged, and you have removed OH and H and have created an alkene. So there was another implied hydrogen there, if that helps to draw in, to keep track. So there is still a hydrogen there, and there's still 2 hydrogens here and here. Otherwise, we've lost H2O, loss of H2O, to create an alkene. And clearly, if you create alkenes, you might create alkenes that are both cis and trans, by the way. That's an interesting thing to note. See if we encounter that. I'm not sure if we will. So I just have a few more quick examples on that. And then I want to get to doing some more good examples of the stereochemistry. And so if we create an alkene here, if we want, we can remind ourselves where the carbons are. There. See, that's such an important part, you know, and why I harped on that so early in the course. I think a lot of people are struggling in the class because they're not really seeing this is. When you see this, you should think carbons are all there. There's another hydrogen implied there, another hydrogen implied there, and 2 hydrogens implied there. So if we lose water, we can lose H2O here, and that will bring us to, and remember, So this whole thing is just hanging on unchanged. We create an alkene here. Is there hydrogen there? Common mistake. No. And it's a dead giveaway. There's 5 bonds now at this carbon. So we lost that hydrogen. However, there is still a hydrogen here. We just lost the OH there, and there's still a carbon and 2 hydrogens there. That hasn't changed. So alternatively, you could lose, you could lose OH from there and H from over here. So plus, you get the double bond here instead. So this is the orange product, and this is the yellow product, as we see. So this one's probably favored. And there's actually a rule for that. It is that the alkene with more carbon substituents on it is more stable. That's just kind of a side note, maybe. Alkene with more carbon groups around it. So if you had to choose, so if you're asked, show both possible products, you would show both possible. If you had to choose which one was favored, you'd go with the more substituted alkene. So see, this alkene has 2 big carbon groups on one side and 1 on the other, whereas this alkene has only 1 carbon group on one side and 1 carbon group on the other side. It's actually pretty easy to spot. But as I said just a few minutes ago, it really does all go back to understanding the structures we're looking at and where all the atoms are. This one's pretty easy. So elimination of H2O would create an alkene there. And if we go along with what we did above, you could say alkene on the other side too, but then you look at it for a second and you say, oh wait, these are the same. All I gotta do is flip one over to get the other one. Not always the case, because if other stuff is on here, flipping it changes it. And that's really the key to the next part with all the stereochemistry. 2 versions of things that are not the same. Which is, it's not a new concept since we started off the year showing isomers at a very early stage. Another quick example. So we're going to eliminate basically to form an alkene either between these 2 carbons or these 2 carbons or these 2 carbons, and they're all the same. So, and I forgot my OH. Yay. All right, so one of those 3 can form a double bond, eliminating water. Go back to white. And so pick one, doesn't really matter. The other 2 will stay the same. In this case, see, this is kind of an example of like how if you want to draw everything out with all the atoms shown at the beginning, it might be easier to see where the alkene is created and what is lost. So it's still a loss of H2O, one of these hydrogens here, and the OH. Finally, this one's already drawn out, so you can get, like I've been saying, the double bond could form along this carbon-carbon bond or along this carbon-carbon bond, and that's the 2 possibilities here and here. And the rule above says more substituted alkene is preferred. So I guess you could say major product and minor product. So any questions on the dehydration stuff? After you do, the whole point of doing lots of practice problems is that you start to see the same thing over and over again, basically, and recognize the important parts that are changing, and that in each of these examples, it's the same thing really over and over again. But questions on that? Okay. I just threw in here, this is a good on your own problem to see, this is a good test of your understanding of this. If this molecule undergoes elimination to dehydration, elimination, I guess it is, how many possible products are there? Try that out on your own. That's an on your own rule. Okay, so chirality, super important topic. Normally, and I don't know why the new textbook doesn't emphasize it, but we definitely did always in this course. So there are chiral molecules. The way to spot chirality is carbons with 4 different groups attached. And there's plenty of detail on this in the videos. So if you look at the molecules I have below, and I say molecules because they're 2 different molecules, the only chiral center is right here. If you understand, if you look at this structure and are not immediately intimidated by it, it's not really that big a molecule. You know where all the implied atoms are, or you just take the time to draw it over on the side, you will see that this carbon right here is the only carbon in the molecule with 4 different things attached to it. So this carbon is attached to a CH2 group right here. Looking at what's directly attached to it, it's attached to a hydrogen. It's attached to this whole group that I'm waving at. And another CH2 here. And so you say, well, wait a minute, those 2 CH2s are not different. How is this carbon attached to 4 different things? And the important part is sometimes you'll see immediately that all 4 are different. But in this case, you have to keep going outward to make sure. And so as soon as you go out in these directions 1 more, you find a carbon with an oxygen on it. And instead over here, you have a carbon with no oxygen on it, but another carbon-carbon double bond. So there you find the difference. That's where the difference appears. So first point difference or difference. To identify the chiral carbons. Or the chiral carbon or carbons. So, and I'm going to go through some simpler examples of this, but in this example, once you get out to this carbon and this carbon, you're able to assign priority groups. So first thing is to recognize, find the chiral center, find the chiral carbon. The second thing is to assign priority groups, which is almost all the work of all of this. You have to assign priority groups 1, 2, 3, and 4 to the groups around the chiral carbon. And that's most of the work. Once you've done that, you just look at it and say if it's R and S, R or S, and you're done for the most part. So assign priority groups. That's most of the work. Priority groups. And then 3 is look and see if the groups indicate R or S. And then 4, be able to draw the enantiomer, the mirror image. That's everything in this section. It's most of the topic of videos 2 and 3 and what I'll spend the rest of today's session on, with lots of good examples. Questions on this so far? Okay, interrupt anytime with questions. So on this one, if you believe me that hydrogen is always the easiest priority group to spot, it's number 4 out of the 4 of 4. Usually the number 1 group is easier to spot. I'm gonna go to the later examples first and then maybe come back to this one once we see more of those. So for now, believe me when I say that this is group 1 and this is group 2, everything attached in this direction, and everything attached over in this direction is group 3. And so as that's finding the chiral carbon, assigning the priority groups, do the priority groups indicate R or S? So then as we're looking at them, you have to have with hydrogen, number 4 usually is hydrogen pointing away from you. Pointing away. So is the hydrogen pointing away from us? Yes. So then as we're looking at it, from going from 1 to 2 to 3 is clockwise. From 1 to 2 to 3. And so if it's clockwise, it's R configuration. We would say R configuration. So configuration, we've seen that term before. It's fixed. It's not something that the molecule can rotate out of or flex out of or twist or bend. All of those things are conformations. A configuration is fixed in space. So to change the configuration, you have to detach bonds, switch things and reattach them. But the most fascinating thing about this to me actually is that if you draw the mirror image, so if this is a mirror here in the middle, you can see here that I drew the mirror image pretty well. It's like this molecule here is looking at itself in the mirror. That really does the same thing as switching 2 of the groups. Switching 2 of the groups. So the 2 groups that were switched are here and here next to that chiral carbon. And so by definition, the mirror image where 2 groups are switched is the S configuration. And these are different molecules. And so when you name this molecule, which is actually named carbone, it's going to be R or S carbone. There's 2 different carbones. You can't call them both carbone because the next question would be like, well, which carbone? Because they're different. So you have R carbone and S carbone. So really, this is really going back to naming, but in a much more conceptual, detailed way. So step 1, find the chiral carbon. That's the only one with 4 different things attached. Assign the priority groups. We did that, and I'm going to go into that some more in examples. And definitely videos 2 and 3, look at those. And then as we're looking at them, 1 to 2 to 3 clockwise is R, 1 to 2 to 3 counterclockwise is S. So 4 is pointing away from us. 1, 2, 3. 1 to 2 to 3 counterclockwise is S. And obviously, a digital clock doesn't help. So we're just looking at old-fashioned clockwise, counterclockwise. Counterclockwise S, clockwise R, as long as hydrogen's pointing away from you. And then be able to draw the mirror images like I did here. Okay, questions on that? Oh, and so I almost forgot. So caraway, the scent and spice of caraway is R carbon. The scent and spice of spearmint, pretty different, is S carbon. So think about that. The two molecules that are virtually identical except they're mirror images of each other, our taste buds and our smell receptors in our body can distinguish the difference between them. This is a whole world of really important stuff, which is why this subject has to be covered in this class. Different drugs need to be either R or S. There's examples of drugs that were prescribed as a mixture of R and S. One example in particular, one of the compounds had the beneficial effects, but the other compound was toxic and caused birth defects. And so it was, and so this was an enormous thing to learn that you can't just give both. They're not the same. Some drugs, only one form is active and the other form could be even toxic or deadly. So hugely important topic. The two forms are called enantiomers. Remember, they're isomers. So R and S are isomers called enantiomers. Enantiomers. So you have the mers from the isomers. The type of isomer they are, enantiomer. Enantiomers. If they're the two forms, so you would call caraway and spearmint enantiomers of each other, or really you should say R and S carbon. Okay, that's kind of like a quick overview of what a lot of what is in the videos also. So here's just back to more simple examples, and I'll do the stepwise thing. So step 1, where is the chiral carbon? There it is. Carbon with 4 different things attached: bromine, hydrogen, methyl, ethyl group. What are the priority groups? So there's rules of priorities. Mostly it's atomic number. So that's straight up from the periodic table. Bromine is the highest atomic number here by far. That's 1. Hydrogen is going to be 4. So 1 and 4, a lot of times 1 and 4 are easiest to spot right away. Carbon and carbon are both the same. So we're trying to decide between 2 and 3. What you have to do is go out further then. It's that same idea of continue outward till you find a difference. So what is connected to this carbon? Hydrogen, hydrogen, carbon. I'm going to write that out right here. Hydrogen, hydrogen, carbon. Out from that carbon. Out from this carbon, hydrogen, hydrogen, hydrogen. H, H, H. We're giving priority to higher atomic numbers. So between these two possibilities, the one that has the carbon is a higher atomic number atom. So that one now is 2, and this one is, 3. We've already signed 1 and 4. Those were easy. 2 and 3 were decided by going out one more bond in all directions from this carbon and this carbon. So that's our priority groups. 1, 2, 3. Is 4 pointing away from us? Yes. So from 1 to 2 to 3 is clockwise. So it's our configuration. Next example is going to be pretty much the same thing again. Easy to spot. 1 and 4. For the 2 and 3, as we go out further, carbon, hydrogen, 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 hydrogen. So this one wins, it's 2. From 1 to 2 to 3 is clockwise, with 4 pointing away from us, yes. So it's our configuration. See, it's not that bad. There are a few more rules of priority though, which I got into at the end of the last video, the very end of the last video. Let's see, we might need to apply that here. Chiral Center is here, a carbon with 4 different things attached to it. You know, clearly a carbon like this one only has 3 things attached to it total. So that puts it out of the running right away. Besides, a double bonded carbon that's flat, geometry, can't be chiral. So anyway, there's only 1 carbon with 4 different things attached to it in this molecule. Easy to spot, 4 and 1, oxygen, hydrogen. Carbon, carbon, you go out 1 atom at a time. Those are the same. But it's pretty easy to see here that attached to this lower carbon, this methyl is H, H, H. Attached to the upper carbon is H, O. So we already can see that that one's going to win. But I'll point out the rule. If it was still tied for some reason, you need a third thing here. And the way to do it is if the carbon is double bonded to an oxygen, you count that as like double oxygens. So you add another oxygen here. So technically we're comparing HHH to HOO, but we already knew that this one's going to end up being 2 and 3. Remember, 1 and 4 we fixed at the beginning. So from 1 is 4 pointing away from us, yes. From 1 to 2 to 3, clockwise, our configuration. Can I draw the enantiomer of this? That's that last one. So the mirror image, if I imagine a mirror here, I'm just going to draw the opposite of what I see. Pretty easy, right? Oh. Our priority groups are already assigned. They're already assigned. 4, 1, 2, 3. 1 to 2 to 3 counterclockwise with 4 pointing away from us, yes. So counterclockwise, S configuration. The mirror image is the S configuration of the R configuration. These are enantiomers. It's really quite amazing because if you put a pure solution of one of these in an instrument called a polarimeter, it will actually hit it with a certain kind of light that makes it rotate positive or negative direction. So you get this like positive number, like positive 70. Then if you put a pure solution of the other configuration in there, it rotates back and goes to negative 70. So that's how these things were originally discovered, how they rotate when they're exposed to certain kind of light. This, you should get better at it with practice. Chiral carbon right there. Priority groups, 4, 1, 2, 3. How did I do 2 and 3 so quick? Carbon, carbon. I recognize right away that this one's going to be attached to hydrogen, 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 which is going to be lower than anything over here. Carbon attached to what? Carbon, carbon. Now the same other rule, if it was needed, which it's not really here, if it's carbon double bonded to another carbon instead of oxygen, you count that double. So you add another carbon there. That's so, and that's really all the rules. I think we've covered every single rule now, and there's really not many, right? So is 4 pointing away from us? Yes. 1 to 2 to 3, counterclockwise, S configuration. Questions on that? Or can I draw the enantiomer? Here's my mirror. H and H2. Priority groups are already assigned. Just look over to the left. 1, 2, 3, 4. From 1 to 2 to 3, clockwise, R configuration. Let me point out one other thing, actually. So if because I said earlier that drawing the mirror image really ends up being the same as switching 2 of the groups. So what happens if I look over here on the left and I switch the NH2, the amine, and the hydrogen? Just going to switch those two. NH2H. The priority groups are assigned 4, 1, 2, 3. But the problem here is that 4 is pointing toward us. But there is a way to get around that. If 4 is pointing toward you, you have actually a couple of options toward you. You would look at it here and say 1 to 2 to 3 is counterclockwise, suggests S, but ... 4 is toward us, which is the opposite of away from us. So therefore, it's R configuration. You just switch it. Really what you're doing there is looking at the priorities, and another way to think about it is if you were behind the screen looking at it from that side, then 4 would be away from you, and you would be looking at it from that side, and it would look like 1 to 2 to 3 clockwise instead of counterclockwise. So is switching any 2 groups going to get you the enantiomer? Yes. Is drawing the mirror image easier? Yes. Right. So, okay, but it does sort of prove the point. I may end up a little early today because I only have a few more examples, but I can preserve time at the end for questions. So here's one more example. Chiral carbon right there. Priority groups, 4 is easy to spot. Carbon, carbon, carbon implied, 3-way tie, right? So this carbon clearly has oxygens attached. This is a carboxylic acid. It's the abbreviation of a carboxylic acid. So you could remind yourself that it's this if you want to. But I think right away from what we've already done, we could say like this is going to be number 1 because that carbon, as soon as you have oxygens, you're done. I mean, this is compared to these other ones that don't. The higher atomic number oxygens are going to cause this to be 1. And then again, now we've seen carbon, hydrogen, hydrogen, hydrogen. That's going to be 3. And this is going to be 2. Carbon connected to other carbons, not just hydrogens. Technically, this carbon is attached to carbon, carbon, hydrogen because there's an implied hydrogen there. So 1 to 2 to 3, as we're looking at it, is counterclockwise. But, so this suggests S, but 4 is toward us, therefore it's R configuration. If I switch the carboxylic acid and hydrogen, put the carboxylic acid forward and the hydrogen back, this ought to end up being S if I did everything right. So 4 priority groups stay the same, 1, 2, 3, 1 to 2 to 3, counterclockwise, S, yep. So with 4 pointing away from us, easier to see. And these really are mirror images. You would just have to have one, instead of side by side, they'd be sort of like one in front of the other. All right, I guess one more example, kind of back to a simpler one, I suppose. Chiral Center right there. I'm going to point out one other thing at the end of this, actually. Thought of something else. 4, 1, easy to spot. Hydrogen, oxygen. CH3, C bonded to carbon, carbon implied hydrogen. This is going to be 2 and 3. 1 to 2 to 3 counterclockwise, but with H toward us, it's not S, it's R. So counterclockwise S, but R because group 4 is toward us. I could draw the enantiomer by switching 1 and 4. So the priority groups are already assigned. 1, 4, 2, 3. 1 to 2, 3 counterclockwise. S, we don't have to do any kind of other thing because 4 is away from us. So, yep, that was R. That's the enantiomer S. So back when we were doing naming, we would call this, well, sort of, that is sort of the beginning of this chapter, but so we would spot the longest chain, 1, 2, 3, or 1, 2, 3, 4. We would call this molecule a 2-butanol. And then there's so numbering for that molecule, in the systematic naming numbering, 1, 2, 3, 4. It's a butane, but there's a OH at 2, so it's a butanol. And then there's a methyl at 3, so it's 3-methyl 2-butanol. And now we know that that is not the complete name. If someone says, do you have any 3-methyl-2-butanol, you would say, well, hang on a minute, is it R or S? So you would say R or S, 3-methyl-2-butanol. And if you had both, it would be R and S. So actually, if you went back to a lot of the naming problems we've done, you would spot chiral carbons in many of those and realize that we didn't even do the full names back then because we didn't do this topic yet. I guess one final thing to point out, and then I'll stop a little early. Back when we were doing alkene reactions, so this is all tied up with reaction chemistry as well eventually. So when, say we had this alkene and we hydrated it, didn't we do maybe slightly acidic water, hydration, and we showed the product being this or this. Probably going to get a little more of this, more likely, but you probably get some of this too. And if you get some of this, this is chiral. So you're probably going to get R and S of this. So you're really actually going to get 3 products. And for synthetic chemists whose career it is to make things, getting 3, 4, 5, 6 products is a horror show. So a lot of organic chemistry time and effort is spent to alter the conditions to get only one of the 3 products, to be specific if possible. Usually that means much more complicated reagents are being used, not just slightly acidic water. You know, this stuff's been around for 300 years, well, probably 1,000 years, I don't know, hundreds of years. New reagents are used to get like only the R product of all 3 of these, for example. So just point that out. Well, Faith, thanks for sticking in with this.
Yeah, thank you.
So there's 20 people in the class and basically 1 attended the Zoom session. You should pin a medal on yourself. Pretty well in the class. I'm going to stop the recording here. Not because, let's see.